Good morning, afternoon, evening, or night. Today, we, the team of Whitefield Global School, present our project about the Patchmate Ideation, or the tuberculosis microneedle patch. It is by me, Soham Das, Devansh Gautam Gaikwad, and Shri Prabhav Allu.
Tuberculosis or TB remains a leading global health challenge, causing nearly 10 million new cases and 1.5 million deaths annually. India carries the highest global burden, reporting approximately 2.8 million TB cases, 27% of the global cases, and an estimated 342,000 deaths in 2022. Despite progress, TB continues to devastate families, particularly in the low income and rural communities. Recognizing this, the Indian government launched the National TB Elimination Program, the NTEP 2025, aiming to eliminate TB 5 years ahead of the global target, an ambitious goal that demands innovative, field deployable solutions.
Now, what are the limitations of the current BCG vaccination? The BCG vaccine, which is delivered intradermally at birth, is currently the only licensed tuberculosis vaccine. While it provides 70 to 80% protection against severe childhood tuberculosis, its efficacy against adult pulmonary TB is limited, according to frontiersin.org. Intradermal injection also requires trained staff, strict cold chain logistics, and precise technique. Many infants in rural or home birth settings miss timely BCG vaccine due to these operational barriers. Multi-dose vials, reconstitution steps, and sharp wastes further strain India's healthcare infrastructure.
This project proposes a dissolvable microneedle patch (DMNP) for transdermal delivery of TB vaccine antigens. The patch enables painless, self-administrable vaccination that targets the skin's dense network of antigen-presenting cells. Painless, as tiny dissolvable needles avoid pain nerves, causes no bleeding, dissolve smoothly, and deliver vaccine evenly. It uses a better TB vaccine administration, improving reach in remote areas while eliminating cold chain and biohazard waste. Preclinical evidence shows microneedle delivery of TB antigens such as AG85B DNA or inactivated mycobacteria, which elicits strong Th1 type cellular immunity and protective efficacy in animal models.
Now, what are the opportunities and next steps? Opportunities include a tuberculosis vaccine patch which could revolutionize immunization by enabling birth, dose, and outreach vaccination without needles. It can also increase coverage in rural or tribal areas by allowing community health workers to administer vaccines safely, even to homeborn infants. The patch format may improve patient acceptability as there is no pain or needle phobia and eliminate sharp disposal concerns, reducing health worker risks. If formulated thermostable, it could greatly ease storage and distribution challenges in hot climates and would reduce cost by 30 to 40%. Enhanced skin immunogenicity might even allow dose pairing, where stretching limited antigen supplies. Cumulatively, these advantages could significantly boost India's tuberculosis elimination efforts by ensuring early life vaccination is not missed.
Aligned with Atmanirbhar Bharat and the NTP 2025 goals, this project drives domestic innovation and manufacturing self-reliance. It aims to co-develop polymer-based microneedle arrays and thermostable tuberculosis vaccine formulations through Indian clusters like ICMR and IIT Madras Nanopharm, and Bharat Biotech using the droplet extension technique. It also advances local technology, ease of delivery, and healthcare democratization.
Patch composed of. A tuberculosis vaccine microneedle patch comprises a dense array of micron-scale dissolvable needles made from soluble biocompatible polymers such as PVP and hyaluronic acid. These microneedles are loaded with tuberculosis vaccine antigens and necessary excipients. Possible antigen cargo includes inactivated mycobacteria, recombinant tuberculosis protein subunits, DNA or RNA vectors, or novel tuberculosis vaccine candidates formulated with stabilizers and adjuvants. The patch has an adhesive backing to affix it to skin, often on the upper arm or thigh, and is packaged as a sterile single-use unit. Packaging includes desiccant and protective envelopes to maintain dryness and stability. Unlike prefilled syringes, the patch is solid state and typically thermostable when properly formulated.
The microneedles painlessly pierce the stratum corneum, and the microneedles completely dissolve in the epidermis and upper epidermis, releasing the TB vaccine antigen directly into the skin. Skin-resident Langerhans cells and dermal dendritic cells capture the antigen. These antigen-presenting cells then migrate to nearby lymph nodes and present TB antigens and T cells. This process simulates a Th1 polarized immune response categorized by interferon gamma and other cytokines, which are critically for controlling TB infection. Indeed, studies report that microneedle delivery in the mycobacterial antigens induces strong IFN gamma, TNF alpha, and IL-2 responses in CD4+ and CD8+. T cells, a detectable humoral response, anti-mycobacterium IgG, is also generated by patch vaccination, especially at high antigen doses. Notably, microneedle immunization can produce immune system responses comparable to or exceeding those from conventional injections.
Now, there are two manufacturing routes that we can do for the following. There is batch casting, where a homogeneous water-soluble polymer antigen formulation is poured into precision molds, or additive on-demand fabrication, where each needle is built as a dissolvable antigen matrix via 3D printing.
Comparative advantages of DMNP over established options. While BCG has established safety, low antigen cost, it is limited by its requirement of cold chain, trained staff, sharp waste, and limited adult efficacy. For M72, it is good at adult efficacy, however, it is limited by its requirement of injection, cold chain, complex, and it is the low India fit. However, our option, the tuberculosis DMNP, has strengths including that its